Hi everyone, welcome back to Introductory Physics, day 17. Yes, yes. We only have 2 weeks left of our class, which is pretty crazy to think about. We are flying through some things. So I know that last week there was a question about the pacing of this class compared to like your regular Physics 1 class at a college level. And I will say that this class probably goes, well, it definitely goes faster than a regular Physics 1 class would go because we're trying to cover the entire semester in just 6 weeks instead of like 16 or 17 weeks. But at the same time, the topics that we have talked about so far are really just like skimming the surface of each topic. There are definitely aspects that I have not addressed for each chapter because of time and because a lot of you have never taken physics before. So even though we are going at a faster pace, we're not going as in depth as you will in Physics 1 at FIT. So just keep that in mind. If you feel like you're drowning a little bit because we're going through things so quickly, don't worry, it will feel slower at FIT. But at the same time, you'll also have other classes to juggle at FIT, so um, just keep those things in mind. But I am glad that you guys are hanging in there for this, and it's always better to be introduced to these things before you have to take it for credit and pay for it at FIT. If you're dealing with other classes now as well, then that's great practice. Good for you. Keep up the great work. But anyway, we are moving on today into chapter 8, which is momentum, impulse, and collisions. So we'll probably go through this in the next, well, today and tomorrow, and then move on probably on Wednesday. We'll see how things go. But this is another pretty significant topic in Physics 1. So we'll do a lot of examples in this aspect of physics. All right, so let's jump into that. Previously, we've talked about Newton's laws of motion. So his first law, the law of inertia, an object in motion tends to stay in motion, an object at rest tends to stay at rest unless acted upon by an outside force. Newton's second law, force equals mass times acceleration, more or less. And then Newton's third law, for every action force, there's an equal and opposite reaction force. So we talked about those a couple of weeks ago. And those equations can be really helpful for solving a lot of different types of problems. We can even relate those to energy and use energy to solve even more different kinds of problems. But sometimes those two things still aren't enough to solve every problem that we'll come across in physics. So there are a lot of questions involving forces that we can't just apply F equals ma to and get a nice, simple solution. So these would be questions like, when an 18-wheeler collides head-on with a compact car, what determines which direction the wreckage moves after the collision? When you're playing pool, how do you decide how to aim the cue ball in order to knock the other balls into the pockets? And when a meteorite collides with Earth, how much of the meteorite's kinetic energy is released in the impact? Those are questions that we haven't been able to answer up until this chapter. But we should be able to answer them at the end of chapter 8 once we know more about momentum, impulse, and conservation of momentum. And the reason is we don't actually need to know anything about the forces to answer these questions, which seems kind of weird that you don't need to know about the forces, but you really don't. So let's learn about those things. All right, momentum. And there are different kinds of momentum. There's linear momentum and angular momentum. So linear momentum refers to, of course, objects that are moving like in straight lines. And angular momentum refers to objects that are rotating or moving around in a circle. And we'll get into that later this week when we do chapter 9, which is rotational motion. So for now, whenever I say momentum I'm specifically referring to linear momentum. All right, the symbol that we give momentum is lowercase p, not lowercase m like you would kind of expect to do. And that's because we already use lowercase m for mass and for meters. We don't want to use it again for a third thing because that's just excessive. So we just pick momentum to be lowercase p. And there's probably some like technical reason why they did that, but I don't know it. So you'll either see it written as a bold P or a P with an arrow over top. What is that symbol, the arrow over top? What does that mean about momentum? We've seen that symbol before. Yes, it is a vector, right? Momentum is a vector. So anytime we see a quantity or a variable with an arrow over top, it means it's a vector, so the direction is important to consider. We have to consider it. The direction associated with the quantity. But you'll also see me writing it just as a lowercase p, and that's pure laziness on my part. I do apologize for that, but it is what it is. The equation for momentum is P equals mv. So m is mass, v is velocity. You'll see velocity is also a bold letter in this equation because remember, velocity is also a vector. But that means that physics defines momentum as the real MVP. But okay, anyway, that's a really important equation for you guys to remember, and it's nice and simple, so yay, that's great. Okay, the units of momentum are kilograms times meters per second, right? Because mass we measure in kilograms, velocity we measure in meters per second. So if you multiply those things together, you get kilograms times meters per second. And we actually don't have another fancy, like we don't rename this as something else. If you remember in energy, we had like I just can't even think of units anymore, but we renamed it as joules. Let's see, force times distance, so newtons times meters. We renamed that as joules, and we just don't do that for momentum. Again, I don't know why. I don't know who decided not to do that. So anytime you write an answer dealing with momentum, you have to write out kilograms times meters per second, which is just really tedious, but it's got to be done, apparently. And like I said, it is a vector, so direction matters. Okay, usually, at least in this class, usually momentum is conserved, but not always. We'll do some examples, well, we'll do plenty of examples where momentum is conserved. But just keep in the back of your mind that momentum is not always conserved. If there are outside forces that are acting on your system or on your object, then momentum may not be conserved. So just keep that in the back of your mind as we go through these problems. Like I said, most of the problems that we will do together, momentum will be conserved. And I'll probably save the not conserved problems for your other physics classes that you'll have to take. But anyway, it'll be great. We often express the momentum of a particle in terms of its components. Again, remember, it's a vector, so each direction is significant. But the momentum in the x direction we'll write as mass times velocity in the x direction. Remember, your mass doesn't change whichever direction you're moving in, so it's not like m sub x times v sub x, because your mass is always the same. But the same basic idea goes in the y direction and the z direction if you're dealing with 3 dimensions. We just are only concerned with the velocity in that particular direction, so each of the components. And sometimes we refer to momentum as the quantity of motion, but it's kind of weird to describe it like that. I've also heard it described as inertia in motion. So like If we remember Newton's first law, an object at rest tends to stay at rest, and an object in motion tends to stay in motion. That phrase right there, an object in motion tends to stay in motion, is really what we're referring to when we talk about momentum. It's that inertia in motion or quantity of motion. So try to remember that as we go through this. But again, I think that's kind of a strange definition, but that is the original definition that was proposed for momentum. So what I want you to do, just real quick, using that MVP equation, I want you to try to solve this problem. What is the momentum of a 900 kilogram car moving northeast at 20 meters per second? Go ahead and give this a quick try. Try to do it in your head if you can. All right, so let's think about this. It's really actually a fairly simple example. So here is our car, and it's moving northeast at 20 meters per second. So momentum, P equals mv. The mass is 900 kilograms, the velocity is 20 meters per second. So our momentum is 18,000 kilogram meters per second. Hooray! Is this answer complete? Are we good to move on? No, Gabriel, what is missing from our answer? The components. Okay, in other words, the direction, right? We need to know what direction is happening here, right? Momentum is a vector, so our answer is not complete yet. We need to add the direction in to our final answer. The momentum is 18,000 kilogram meters per second northeast. We can't necessarily calculate the components because we don't have the particular angle unless you're assuming that northeast means exactly 45-degree angle. But, you know, in that case, the magnitude of our, like even if we broke it down into our components, our x component and our y component, when we find the magnitude of it, we would still get the same answer of 18,000 kilogram meters per second. And then our angle wouldn't change, it would still be northeast. So this would be our final answer. You can see we have the value, the units, and the direction, and you need all of those things for a complete answer. Most of the other examples that we'll do, though, our direction is going to be implied by the sign of our answer, just like we've done with forces and things like that, where, you know, up, forward, right, east, those are all of our positive directions, and then down, south, west, backwards, those are all of our negative directions. So if you see a negative sign in our answer, we're just, you know, implicitly stating the direction. Okie dokie. So let's think back to Newton's second law again. We should remember that Newton's second law is not just F equals ma, right? That's the like simplified way to say it, but really it's the sum of the forces, or the net force, equals the mass times the acceleration. That's where that sigma sign comes into play. We also want to remember from way back in, what was that, chapter 2, I think, that our acceleration is our change in velocity over change in time, or the derivative of velocity with respect to time. Remember, that's what this notation dv over dt means. We're taking the derivative, or the slope of our graph. So if we know that's what acceleration is, then we can plug that into our Newton's second law equation. And we'll get the sum of the forces, or the net force, equals mass times dv dt. Well, mass is a constant, so we can put it inside the derivative, we can move it outside the derivative, and it does not change our final answer. So if we move it inside the derivative, then we see d dt, or the derivative of parentheses with respect to time, So the derivative of mv with respect to time is equal to our net force. And we just learned that that quantity, mv, is momentum. So Newton's second law is really also saying that the net force equals the change in momentum over time, dp dt. So from this, we can state, I guess, that a rapid change in momentum requires a large net force, but a gradual change in momentum requires less net force. So that's why when you're thinking of like car safety, that's why we have airbags in our cars, is to increase the amount of time that you are changing your momentum in the event of a car crash. Instead of like smacking right into the steering wheel, you have this nice little cushion that increases that amount of time, and so you experience a smaller force on your body. So that's cool and helpful, I guess. Have airbags in your car, people. Just do it. I don't even know if you can buy cars without airbags anymore. I think they're like, you have to have them there kind of thing. Okay. Anyway. This leads us to the impulse momentum theorem. So remember, last week we were talking about energy, and specifically kinetic energy also depends on your mass and your velocity. We call it speed because energy didn't care about the direction, but it is a V in our equation. So both momentum and kinetic energy depend on the mass and the velocity. And so sometimes it can be kind of difficult to see the difference between these things and like when to use which one, other than like obviously in one equation V is squared and in the other equation it's not squared. It's like mathematically we can see a difference, but physically it's a little bit more difficult to see the difference usually. So when we want to see the physical difference between these two ideas of momentum and energy, we first have to define something called impulse. The impulse is the product of a net force times the time interval during which that force is acting. And for now, we're just going to consider a constant net force. But there are some times where you can have a changing net force, and we have to use a slightly different equation for impulse when we're dealing with a net force that changes over time. But impulse has the symbol capital J. I don't know why. I mean, I is like other things, but it's annoying. Anyway, impulse, capital J. Again, usually you'll see it written as a bold J or a J with an arrow over top because it's a vector. Direction matters. But you'll also see me potentially being lazy sometimes and not putting the arrow over top. Bad teacher moment. I'm so sorry. So when we're thinking about the equation for impulse, there are really three ways that we can consider this. And they look a little intimidating at first, but we'll talk through them. So our first way to consider this, impulse equals, remember the sum of our forces is our net force times our change in time. So our second time minus our first time. That's the same thing as saying the sum of our forces times delta t, our change in time. And also remember, since the sum of our forces is also called net force, I rewrote it for you that way in case your textbook or your professor writes it down in that manner. But they all mean the same thing. It's your net force times your time interval. That's your impulse. You may also see it written this way, where, and I think we've talked about this before, but it's been a long time, that like elongated S shape is called an integral. And so if we take the integral or the area under the curve from one time coordinate to the next time coordinate, so from T1 to T2, So the integral of the net force with respect to time, dt. That's another way to consider it. And really the difference between those two is it's very slight. It's the same basic idea, but when we use them is different. And really, we use the first one when we're dealing with a constant net force. And we use the second one when we're dealing with a changing net force. That's really the only difference between those two. But again, I'm not really teaching you about integrals so much in this class. You'll learn about them from your professor if you need them. So I plopped it there just so you can see it, but for pretty much every example that we do, we'll be dealing with a constant net force, so we would use this first equation. We could also, though, use this third equation where impulse equals the change in momentum. So final momentum minus initial momentum. So yeah, number 1 and number 3 are the two equations that we will be using for impulse. We won't really use equation number 2. And the unit of impulse is again kilogram meters per second because it's a change in momentum, and momentum's units are kilogram meters per second. So this third equation really is what's known as the impulse momentum theorem. And I don't think I actually put boxes around these equations, but they are ones that you would want to write down on an equation sheet in a quiz or a test. They're pretty important, and we'll be using them in pretty much every example that we do for today. Okay, so we saw that second equation. This is just to refresh your mind because it's been a while since we talked about, well, since I introduced integrals to you. But if you think back to chapter 2 when we were talking about our motion graphs, so going from a position time graph to velocity time graph, or velocity time to acceleration time graph, you take the slope of the line at each point, and that's how you can go down our stack of graphs. But to go from an acceleration graph to a velocity time graph, you take the area under the curve. Same thing to go from velocity to displacement. You take the area under the curve, or the integral. So I just wanted to show you these graphs here for when our net force is not constant. So if our net force changes like this red curve over time, then the impulse is the area underneath of that curve. We could also calculate net force by using an average force over that time interval. And it would still give us the same area under the curve. In this case, it's a rectangle for our average force. But it would give us the same impulse if we use that average force times our time interval instead of our varied net force, our changing net force. This other graph over here with the blue and the yellow curves, this show the effects of the time interval on our force. So in both of these cases, we have the same impulse. We have the same area under the curve. But if we have a really short time interval that this force is acting, then it's going to be a really big force. And if we can spread that force out over time, then our force is a lot less. So that would be like the airbag example, where we can spread out that force over the most amount of time, and then we end up with, you know, a smaller maximum force. Okay. So let's do some examples using impulse. Okay, suppose you throw a ball with a mass of 0.4 kilograms against a brick wall. It hits the wall, moving horizontally to the left at 30 meters per second, and rebounds horizontally to the right at 20 meters per second. So in this case, we are ignoring the force of gravity pulling it down. We're just assuming it's moving horizontally. So which equation in this case would be the best to find the impulse? Remember, impulse is capital J. Which one would be the best one to choose? What do you guys think? Right. So since we don't have the time interval, it's really not helpful to use either number one or number two because those both deal with time. But we do have velocity, and we know momentum, P equals mass times velocity. So we're going to choose the third equation as the most helpful one in this case to find the impulse. So let's find the impulse of that net force on the ball during this collision with the wall. So I'm using the subscript 1 to mean initially and 2 to mean final. In other examples, I'll use I and F just so you see both notations because different books and different professors use different things. But initially, so our first momentum is mass times our initial velocity. So mass, 0.4 kilograms, times our initial velocity. It's initially moving left at 30 meters per second. So we do have to include that negative sign because again, our standard rule of thumb is choose right to be positive and left to be negative. So our momentum in this case is negative 12 kilogram meters per second because it's moving to the left. Our final momentum would be mass times our final velocity. And our final velocity is moving to the right, so that's positive 20 meters per second. So that gives us a final momentum of 8 kilogram meters per second. Impulse is the change in momentum, so that's momentum 2 minus momentum 1. So 8 minus negative 12, or 20 kilogram meters per second. Now you may also see that written as Newton's times seconds because of that first equation for momentum. Remember, impulse equals force times the change in time. So Newton's times seconds. So I wrote them both ways for you just so you can see that those units are equivalent. But either way would be totally fine. And I would say, I know I put the green box around Newton's times seconds, but in this case, I would rather that you choose the kilograms times meters per second, just because that's dealing with the variables that were actually given. If the ball is in contact with the wall for 0.01 seconds, find the average horizontal force that the wall exerts on the ball during the impact. So now we do have time, and we can use that first equation for impulse. Again, I got lazy with my arrows, so I was running out of time. I'm very sorry about that. But impulse and force are both vectors, so the direction is important here. But our force, our average force, we calculated just on the last slide. So I'm sorry, not our force, our impulse, we calculated on the last slide. And that was 20 kilogram meters per second, or 20 newtons times seconds. So we divide that by our time interval of 0.01 seconds, and we get an average force of 2,000 newtons. That's a lot of force. It's positive because the force is pointing to the right. Right, that's like the normal force of the wall against the ball. It's pushing it back to the right. So last step of this, find the acceleration of the ball during this time interval. There are actually two different ways that you can do this. So I have two different colored boxes there. I'm going to show you both ways that you can do this. And this is a great way to check your answer and see if you got the right thing. So our first method, if we remember that the acceleration is the change in velocity over the change in time, or v2 minus v1 over a change in time, then we just plug in our velocities and our time. Right, our final velocity is positive 20. Our initial velocity is negative 30, so 20 minus negative 30 divided by our time interval of 0.01 seconds. That gives us an acceleration of 5,000 meters per second squared. Yikes, right? Remember, the acceleration due to gravity is 9.8 meters per second squared. So if you look at this and you think to yourself, like, is this even possible? Is this like, did I make a mistake here somewhere? Which I initially thought to myself at first because this just seemed like a ridiculous acceleration. I went ahead and tried it with the second method using Newton's second law. So our average force we just calculated on the last slide to be 2,000 newtons divided by our mass, which was 0.4 kilograms. And again, I got an acceleration of 5,000 meters per second squared, which just seems ridiculous if you ask me. But it's verified by both of those methods. So man, this ball is undergoing an extreme acceleration here as it hits that wall. But that makes sense because it's traveling really, really fast as it's going towards this wall, like 30 meters every second. Remember, a meter, for you non-metric thinking people, a meter is approximately a yard, which is 3 feet, which is approximately 36 inches every second. That's it. That's fast. So it's traveling really fast towards this wall. Yeah, Gabriel, that's a really good thing to point out. The thing is, in reality, this acceleration lasts for just a fraction of a second. Yeah, 0.01 seconds. So quite a fraction of a second, which is important. Yeah, if not, we would die playing catch. I would not want to be that wall. Yikes. There's a reason why I don't play professional baseball. I mean, this is one of them. There are lots of reasons why I don't play professional baseball. I'm not good. Okay. Anywho, are there any questions about this example? Nope, none from Gabriel. Okay. All right. As always, if you have any questions, feel free to type them in the chat, and I will keep trying to monitor them as we go. So onward and forward. Example 3, impulse on a rocket. Because who doesn't love rockets? A 4,000 kilogram rocket is traveling forward at 11 meters per second. Its reaction control system fires, imparting an impulse of 8,000 kilogram meters per second to the right. So initial question for you, will the x component of the velocity change? And will the y component of the velocity change? What do you guys think? All right, so let's think about this. Here's our rocket. It is traveling forward at 11 meters per second, and something comes along and tries to boost it to the right. So it gives it an impulse rightward. This should change our x component of its motion, right? If you are walking forward and somebody goes and pushes you sideways, you're probably going to start falling or moving somewhat sideways as well, right? There's no other force that's counterbalancing that. So it is going to change the x component of its velocity. But if we're pushing him, sorry, not pushing him, pushing the rocket to the right while it's moving forward, that's not going to change its forward motion necessarily because we're not boosting it forward or backwards or anything like that. We're just boosting it to the side. Gabriel, you say, I push him back. Yeah, but like literally, according to Newton's third law, you do push him back. It's just your body pushes his hands back with the exact same amount of force. I'm totally sure that's what you meant by that. Anywho, our x component, yes, it does change the velocity. Our y component, no, it does not. Because remember, just like in projectile motion, our x and our y components of motion are separate from each other, and one does not affect the other. Okay, so how do we find those x and y components of the final velocity? Well, we're going to use the impulse momentum theorem like we have been doing. Y velocity is constant since there is no impulse in that direction. So its initial velocity is the same as its final velocity, which is 11 meters per second. Yeah. The x velocity will change because we are giving it an impulse in the x direction. Impulse, remember, is the change in momentum, so final minus initial. So that impulse we know is 8,000 kilogram meters per second. And we know momentum is mass times velocity. So our final x velocity is going to be our mass, 4,000. And so it'll be 8,000 divided by 4,000, which gives us a velocity of 2 meters per second. So that is our final x velocity. Initially, it had no x velocity, and now it's ending up with 2 meters per second x velocity. All right, so now if we want to find the actual magnitude and direction of the rocket's final velocity, we're going to ignore gravity and air resistance for this, as typical. But anyway, we found our components. Let's put them together to find the magnitude. Remember, these bars, these absolute value bars around a quantity, mean the magnitude, or just the size of it, not including the positive or negative for the direction. But we learned how to find the magnitude of our vector addition in chapter 2. One or two? Can't remember exactly, but like the first week of class. So there's our equation, which should be familiar, the Pythagorean theorem, right? It's the square root of our x component squared plus our y component squared, which gives us a final velocity of 11.2 meters per second. And since velocity is a vector, we need that direction associated with it. So again, from our talk about vectors way back in the beginning of this class, our direction is the inverse tangent of the y component over the x component. So inverse tangent of 11 over 2, which is approximately 80 degrees. So the rocket is moving forward, it gets this impulse to the right, and it ends up kind of skewing its motion off by that little angle. So that 80-degree angle is measured from our positive x-axis, not from our positive y-axis. So this little angle in here is 10 degrees, but this bigger angle from our x-axis is what is 80 degrees. Okay, any questions, comments, concerns about this example? Feeling good? All right. Example number 4, kicking a soccer ball. This one is similar to example 3, but this time we're not kicking the ball at a really convenient right angle, or kicking it at a different angle. So a soccer ball has a mass of 0.4 kilograms. Initially, it's moving to the left at 20 meters per second, but then it's kicked and given a velocity of 45 degrees upward and to the right with a magnitude of 30 meters per second. Find the impulse of the net force and the average net force, assuming a collision time of 0.01 seconds. So let's take a look at this. Our initial x velocity is negative 20 meters per second because, again, it's moving to the left. Left is negative. And it's initially rolling on the ground. It's moving horizontally. So our initial y velocity is 0. But then we kick it at this angle. And so it'll fly off at this 45-degree angle. So we are going to have to break this down into the components using our trig functions sine and cosine. So our final x velocity is our final velocity of the ball, the hypotenuse of our triangle, times the cosine of our angle. And again, I always recommend that you draw a picture so you can see for sure whether or not you should use sine or cosine. We saw a couple examples, not last week, but the week before, maybe it was last Monday, where our x component actually did not use the cosine, it used the sine. So always draw a picture to make sure you know which one to use. In this case, it is the cosine because our x component is adjacent to our angle. So once we plug all of that in our calculator, we get a final x velocity of 21.2 meters per second. And due to the nature of 45-degree angles, the sine and the cosine of a 45-degree angle is the same thing. So we end up with the same y component as x component. Our impulse is our change in momentum. So remember, momentum is mass times velocity. So that's mass times our change in velocity. Mass is 0.4 kilograms. Our change in our x velocity is 21.2 minus negative 20, which gives us an impulse of 16.5 kilogram meters per second in the x direction. And we do the same sort of thing for the y direction, except we use our y velocities, of course. And so we end up with a y value for our impulse of 8.5 kilogram meters per second. So those are our components. That's not the magnitude of the impulse. If we wanted to find the magnitude of the impulse, we would do just the same thing we did in example 3. Using the Pythagorean theorem, we would take the square root of our x component squared and our y component squared, and we could find our magnitude that way. But I'm not going to for the sake of time and space. So we wanted to also find the average net force that's acting on it. Remember the impulse momentum theorem, that first equation for it, J equals F times delta T. We take that equation, rearrange it for average force in the x direction. So we'll use our impulse in the x direction over our change in time, which ends up being 1,650 newtons. And our y component of the average force, same idea, y impulse over change in time, which is 850 newtons. There they are again. So now I'm going to find the magnitude and direction of our average net force. And again, you can do the same thing with impulse if you choose to. But same idea, right? Our magnitude is using the Pythagorean theorem. The square root of our x component squared plus our y component squared. That gives us a final average force of 1.9 times 10 to the 3 newtons, or 1,900 newtons. It's a pretty good kick. And the direction of our force, again, uses the inverse tangent of the y component over the x component. So that gives us a direction of 27 degrees. So that's kind of an interesting thing that's happening here. Our ball is flying out off of this kick at a 45-degree angle, but we applied the kick at a 27-degree angle. So why is there a difference between those two angles? Is that weird? Is that a mistake? Or does that actually make sense? So think about our last example with the rocket, right? It was traveling at a, well, forward, and then we gave it this kick at a rightward direction, and then it ended up traveling at this 80-degree angle. It didn't travel straight to the right. And we didn't really have any issue with that, just mentally thinking about it. Or if you did, you didn't say anything, so I just assumed you didn't. But it's basically the same idea here, right? It makes sense that the rocket is going to continue moving somewhat forward, even though it's being kicked to the side, and that just shifts the angle a smidge. It's the same basic idea here. The ball is moving to the left, and we kick it, but it's still moving somewhat to the left, so it's going to carry its trajectory somewhat more to the left than um, than it would. The ball is moving, right? If the ball were sitting still and we kicked it at a 27-degree angle, then it would fly at a 27-degree angle. But since the ball is moving, it has that momentum to the left that carries that angle more to the left, more, what is that, counterclockwise than our kick actually is. Does that make sense? Oh, okay, good. If it doesn't, then feel free to hang out with me um, after we talk through this, and I'll try to explain it in other words. But yes. We have a question here. How did you find n? So, Marco, which n are you referring to? Both. So you mean like the n that's at the end of these numbers here for our forces? The n that's at the end of these numbers is our unit newtons, because that's what we measure force in. How did we find out those numbers? Let's go back a slide. These numbers I took directly from the bottom of this slide, and that's from the impulse momentum theorem, which the way that we had it written out initially was J equals F times delta T. So I took that equation and I rearranged it to solve for force, because that's what we needed to find here. We needed to find the average net force. So in that case, force equals impulse over change in time. And yeah, for the sake of running out of space down here, I didn't actually plug in the numbers, but Jx was the 16.5 kilogram meters per second, and our change in time was from the problem statement 0.01 seconds. So 16.5 divided by 0.01 gives us 1650 newtons, and then vice versa, well, not vice versa, but similarly for our y component. Okay, that's a good question, because I didn't explicitly write it out. So good question. Any other questions before we move on? Okay, I'm not seeing any questions. So of course, if you have them, feel free to type them in and I will address them as best I can. But I want you to give this a try. So I wrote up there at the top are equations for impulse, the two different ones, so change in momentum and net force times our change in time. And then I also wrote up there the equation for momentum for you. But I want you to do is look at these situations, and I want you to put them in order from largest to smallest in terms of the impulse of our net force. So take a couple of minutes, think through this. Which situation ends up with the largest impulse, which one has the smallest impulse, put them in order. Okie dokie. So that may or may not have been enough time for you to think through this. But either way, we're going to start going through this for the sake of time. And I don't have a slide that shows the math of this, so we'll just talk through it. And if you want me to, I can add in a slide that shows the step-by-step math stuff, calculations, but follow along with me. Okay, so the one that has the most or the largest impulse is E. And so the way we find the impulse in E is that change in momentum method. So we know that it's initially moving east at 25 meters per second. So our initial velocity is positive 25. And then eventually it changes direction completely and ends up moving west at 25 meters per second. So that would be negative 25 meters per second. Okay, so our change in velocity there is 50. Sorry, 50. And so we end up with an impulse of, what was it, like 50,000 kilogram meters per second. And I will put in there a math slide for you. Sorry, I don't have it right now. But the fact that the mass of the car is 1,000 kilograms is an important thing to note. So we have a change in velocity there of 50 meters per second times our mass of 1,000 kilograms. So that's 50,000 kilogram meters per second is our impulse there. For our next biggest, we actually have a tie. A and B are both equal in magnitude for their impulse. And we also, for those two, use that change in momentum method. So for part A, the car is initially moving east at 25 meters per second, so a velocity of positive 25 meters per second. And the fact that it comes to a stop is important, but the fact that it does so in 10 seconds is not important when we use the change in momentum method. So when we're stopped, that means our final velocity is 0. So that's a change in velocity of 0 minus 25 or negative 25 meters per second. And again, the mass of the car is 1,000. So if we look at our momentum equation up there, mass times velocity, so 1,000 kilograms times negative 25 meters per second, which is our velocity change, is negative 25,000 kilogram meters per second. But it asks for the magnitude of the impulse. So the magnitude of that would be positive 25,000 kilogram meters per second. Same idea for B, right? It's initially moving east at 25 meters per second and comes to a stop. That's all the same. This time it does so in 5 seconds, but we don't use the time when we use the change in momentum method. So again, our magnitude of the impulse is 25,000 kilogram meters per second. And then in third place, we have both C and D. They have the same magnitude for their impulse. So in part C, the car is initially at rest, so velocity 0. And then a 2,000 Newton net force toward the east is applied to it for 10 seconds. Well, since in this case we have a force and a time, we're going to use the net force times change in time method so that we don't have a final velocity, so we can't really use the change in momentum method. So our 2,000 net force times our change in time of 10 seconds gives us 20,000 Newton seconds or 20,000 kilogram meters per second as an impulse. And then with the next one, part D, the car is initially moving east at 25 meters per second. And again, a 2,000 Newton net force toward the west this time is applied to it for 10 seconds. So we again have a net force and a time. Let's use that method. Net force, 2,000 newtons. It would be negative because it's to the west, but again, we're dealing with the magnitude for impulse, so the negative doesn't really matter. And then our change in time is 10 seconds. So 2,000 times 10 is again 20,000 newtons times seconds. Okay, so I know that was probably a little bit confusing, just me talking through it instead of actually seeing the math written out. So sorry about that. I will include a math slide for you. I'll create that as soon as class is over, and then I'll post this to Canvas so you can take a look at it if you need to do so. Okay. Just a couple quick things before we finish up today. Momentum is important when you're looking at single objects, like we have done so far, right? A single rocket or a single ball, etc. So obviously momentum is important when we're concerned with one object at a time, but it's, I would say, especially important when we're dealing with multiple objects that are interacting with each other. Like the example of kicking a soccer ball. If we have two or more different objects that are interacting, then we really have to pay attention to what is happening with the momentum. And there are a couple of different ways that objects can be interacting with each other. They could either be colliding, so two or more things come in and hit each other, or they could be, the book calls it recoil, but that's a little bit misleading. They could be separating, basically is the easier way to think about that. So two things start off together and then they separate, possibly explosively. So things like firing a gun or blowing up a firework or what have you. Those are considered recoil cases. For any system, the forces that the particles in the system are exerting on each other are called internal forces, because we have these particles that are interacting, and so when we just look at the interaction forces, those are internal forces. If there are other forces that are exerted on those particles or on the system by some outside thing, then those are called external forces. And when there are no external forces, then we say we have an isolated system and we're only dealing with internal forces, which is always the nice, convenient case, but not really the realistic, real life case. So we'll look at both ways. Not today, but tomorrow. So when we are dealing with multiple objects at once, it's important to consider the total momentum of the system. And the total momentum of the system is a vector sum, because remember, momentum is a vector, the direction matters. So it's a vector sum of the momenta, which is plural for momentum, of each individual particle. So we give this total momentum the symbol capital P. Remember, lowercase p is the momentum of a particular object. But when we have more than one object, we add those all together and get capital P total momentum. So there's that plus dot, dot, dot in the equation, just because we don't know how many objects we could be dealing with. It could be a very large number, or it could be just two. The time rate of change of the total momentum is 0. And so the total momentum of the system is constant. This would be if there are no external forces, so our isolated system case. Even though the momentum of each individual particle can change, our total will stay the same. That's called conservation of momentum. So if you think about conservation of energy and conservation of momentum, they're very similar ideas, right? With energy, we could have energy changing from kinetic to potential. And so the amount of kinetic would decrease, but the amount of potential would increase. But the total amount stayed the same the whole time. Same basic idea here for momentum. We can kind of transfer momentum from one object to another, where one would decrease its momentum and the other would increase its momentum. but the total amount in the system will be the same all the time. Conservation of momentum. And so our equation for that is final momentum equals initial momentum. It's a constant. You're going to have the same total momentum at all points. This is true if the vector sum of external forces on a system is 0, right? So if there's no net external force, conservation of momentum applies. And when we're dealing with conservation of momentum, remember it's a vector, so we can think about it in terms of its components as well. That means the momentum in the x component is conserved, momentum in the y component is conserved. If you have z component, momentum in the z component is conserved. So in each direction, you'll have a constant value of your total momentum. And unlike conservation of energy, this is valid even if we're dealing with non-conservative forces. So things like friction and air resistance and applied forces and all that jazz. When we were dealing with energy, energy was only conserved if we were dealing with conservative forces like gravity, for example, where there's that two-way relationship between different types of energy, and energy wasn't like lost to something where it couldn't be gotten back. But momentum doesn't matter. Any kind of force, conservative, non-conservative, totally valid. So sometimes both momentum and energy are conserved, and sometimes only momentum is conserved. But for our purposes, momentum will always be conserved. And again, I had inferred previously that there are times where momentum is not conserved, but we will not get into that. Definitely not today, most likely not tomorrow, maybe not at all. But anyway, that I think wraps up our discussion for today. Do you guys have any questions about this stuff before we put it into practice and like real life examples starting tomorrow? All good from Gabriel. Okay. Yes, I can go back a slide. There you go. All right, well, if you guys don't have any questions, comments, or concerns, I hope you guys have a great day, and I will see you tomorrow. Bye.